Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Last two classes we have started our discussion on nickel based superalloys. Along this direction we tried to explore the various microstructures that are available in these superalloys, and we have seen that from a different type of strengthening mechanism that are available in these nickel based superalloys. So, today we will be discussing on the physical metallurgy, let us say in terms of microstructure and property relationship in these nickel based superalloys. So, if we like to see the wide range of microstructural constituents that are possible in nickel based superalloys, they are like from the left hand side we have a FCC gamma nickel matrix, where there are many different elements which causes solid solution strengthening. Now, here the dark color region is the gamma nickel phase with some other alloying elements, and these precipitates are, in case of nickel based superalloys, these are gamma prime phase. So, gamma prime is a nickel 3 aluminum phase. Now, if we consider the strengthening by precipitate, so there are two different type of precipitation strengthening available in nickel based superalloys. As I said earlier, one is the gamma prime phase, which is nickel 3 aluminum, another is gamma double prime phase, which is nickel 3 niobium type phase. So, in one case it is a ordered FCC structure which is called as L10, and nickel 3 niobium is D022. Specifically, in case of nickel based superalloys, we only get nickel 3 aluminum. However, if it is iron nickel superalloys, let us say Inconel series, where there is a substantial amount of iron inside, there we get this gamma double prime phase, which is a ordered BCT, body centered tetragonal structure. Now, here if you closely look at the structure or of these Ni3Al, here this is a ordered FCC structure, means the position of the atoms are fixed. Here these empty bubbles representing aluminum, which is sitting at the corner of the cell, and all the face centered positions are occupied by nickel atoms. However, very close to its melting temperature, gamma prime phase, means nickel 3 aluminum, become disordered. So, any position either nickel or aluminum can be found. So, this is let us say a typical nickel 3 aluminum structure. Now, in case of nickel 3 niobium phase, here we get a ordered body centered tetragonal structure, and these are the position of the niobium atom, which is the corner of the cell. Now, the nickel atoms are sitting at the face centering the face centering positions, and this cell is quite a bit large, and this is definitely there is a body centering atom, body centering translation. So, this is a body centered tetragonal structure. Now, besides precipitation hardening, I also said about the grain boundary precipitate, which causes grain boundary strengthening, because at elevated temperature any grain will try to grow because of the diffusion of the atoms. And to stop that, we have some specific carbide and boron which assist nickel based superalloys to survive at higher temperature. Now, here MC stands for a metal carbide, and this is just representing the stoichiometric of the compound M6C or M23C, and M7C3. These are the stoichiometry, where M stands for chromium or molybdenum or titanium or tantalum or hafnium. So, these are the possibilities. Now, there are also some borides which have a stoichiometry of 3,2, let us say M3B2, and they usually appear at the grain boundary region of the nickel based superalloys. Here you can see these are the precipitate of these gamma prime, or let us say gamma double prime phase and so on, and so here these are the precipitate at the grain boundary region. However, these two type of phases which are very much important in case of enhancing the high temperature properties of the nickel based superalloys. Now, there are also some undesired phases evolve due to improper composition selection, or let us say some sort of heat treatment or treatment of the alloy. So, these are the topologically close pack phases, we call it as A x B y. This is just representing A and B are different, two different element, and x and y are their stoichiometry. So, these are topologically close pack phases and they are very much undesirable, and they mostly form at the grain boundary and causes cracking during service life. So, due to improper selection of these elements actually like chromium, molybdenum, tungsten and rhenium, they are if the stoichiometry is not proper, then instead of forming any carbide or they go to the solid solution or going to the precipitate, they form these kind of mu phases or let us say sigma phases. So, one should be careful of selecting a alloy composition and proper treatment to avoid the topologically closed pack phases which deteriorate the properties of the nickel based superalloys. So, these are the wide range of microstructural constituents that are possible in nickel based superalloys. Now, specifically if we look at the gamma prime phase, what is the role of aluminum, that always comes to our mind. Why we are so interested about aluminum? Is it only because aluminum form alumina scale? Is it only the thing? However, if you look at the formation of the enthalpy of nickel and aluminum, so there is some interesting things. So, let us have a look at the diagram here, which is represented here with the x axis with atomic fraction of aluminum, and here is the enthalpy of formation of various phases. So, the dotted line represent actually the gamma nickel solid solution phase, okay. And these are the solid line are joining different stoichiometric compound that form in nickel aluminum system. The first one is of our interest, that is the gamma prime phase nickel 3 aluminum. Now, there is a binary composition aluminum nickel and so on. You can see that up to let us say 0.2 and close to that, the formation enthalpy of the solid solution phase is preferred, and whereas just beyond this composition range, the gamma prime nickel 3 aluminum phase is preferred. Now, if we consider that if we add a aluminum to a nickel lattice, whether nickel aluminum bonds are more preferred or aluminum bond is more preferred or nickel bond is preferred. So, in that case you will find that inside that crystal structure nickel aluminum bonds are more preferred than the nickel or aluminum bonds. So, therefore, there is a very strong degree of chemical ordering that are displayed by this nickel and aluminum system. So, this is the nickel side and this is the aluminum side actually. Now, on the other hand, there is a complete mutual solubility is expected, because if we think about nickel has a FCC structure and aluminum also have a FCC structure. So, we should have a complete range of solid solubility, but it is not in reality, because they form a wide range of different compounds, and there is some sort of directionality of the bonding even though they are metallic, but because of this little directional nature of the bonding and covalent bonding. So, there are many stoichiometric compounds exist in case of nickel aluminum system. So, therefore, the gamma prime phase we tried to understand the role of aluminum in this particular case. Now, if we look at the composition of these nickel based superalloys, there are many different alloying elements has been added so far. Now, let us think about what are the addition of the different alloying elements, like cobalt. Cobalt is always alloyed with the nickel, and chromium is there, molybdenum and tungsten, etc. So, now we should not consider only on nickel aluminum, but let us say we can call it as a nickel aluminum and X. X is basically one of these metal. So, one can always ask if we add a ternary element to a system, whether that will go into the solid solution or it will go to the precipitate or it will form some other phase, what will determine. So, we can have a look at the ternary phase diagram, that will be very much useful, that what are the individual role of these elements. Now, we can simply think about the three cases. Okay. So, let us say a cobalt and platinum, if we consider these two elements, they basically expand these gamma prime phase field parallel to nickel X. What does it mean? Let us say here I have nickel one of the side, and here this is the X, and this side aluminum is going to increase. So, please try to read the ternary phase diagram. If we go from this side to this side, then basically nickel atoms are replaced by X, there is no doubt about it. So, if we look at cobalt and platinum, so the phase field of the gamma prime phase, which is sitting at the nickel 3 aluminum. Okay. So, means basically around 25% here, 25% aluminum is here, because if you look at the atom ratio. Now, from here it basically expand to this direction, extend to this direction. Okay. So, the cobalt, platinum and also copper, they basically extend this phase field towards a direction of the nickel and X this side. So, it simply said that the aluminum concentration, or they do not the addition of cobalt and platinum do not replace the aluminum. Okay. This is very clear. Now, if we look at titanium and tantalum, what I want to mean that this set of elements, if we see, they expand this phase field of gamma prime towards aluminum X axis. So, here this is the aluminum and X axis. What does it mean? That nickel remain constant. Okay. So, if we add indium and tin and tantalum and vanadium and titanium, they will replace aluminum. So, this is very straightforward matter. Now, if we look at the chromium, iron and manganese, so let us say the elements lying here, this region, they usually show some sort of mixed behavior. Okay. And so, now we can understand that these are the element, if we add, then simply it will go to this gamma prime phase and they will extend the phase field. Yes. So, they have some solubility in the gamma prime phase, and it is not very less. You can see it is a quite heavy amount, let us say something like 30 to 40% solubility is existing here. In case of this set of element, it has something like 22 to 23%. Okay. Now, there are also some other behavior we should see, because if we add an element and if it reduces the melting temperature of the hard intermetallic phase, then also it is not useful for making a good alloy, right. So, this gamma prime phase ordering and their ordering temperature basically decreases. Means if we look at the pure nickel 3 aluminum phase, okay, they have a ordering and disorder, order transformation temperature which is very close to the liquidus temperature. Okay. So, there is very little gap. So, from let us say something like 1375 degree to close to let us say 1400 degree centigrade. Okay. Now, if we add this iron, just I like to show the case of iron, it basically make the ordered phase as a disordered phase and decreases the ordering temperature. So, here I have a ordered phase and here I have a disordered phase. So, ordered phase is preferred because we will see later on they are quite linked with the strength of that particular precipitate. Okay. Now, let us look at some other aspect of this gamma prime phase. If we keep on adding element to a gamma prime means nickel 3 aluminum, we expect that the lattice parameter will change, and if lattice parameter changes, then definitely there will be a difference between the lattice parameter of the matrix gamma nickel phase and the ordered gamma prime phase. Yes. So, we can mathematically calculate and experimentally we can also estimate the amount of the mismatch. So, here this is represented by the delta. So, here delta is equal to 2 into a to the lattice parameter of the gamma prime phase minus the lattice parameter of the gamma nickel matrix, and below here these are the summation of these two different lattice parameters. So, here these particular solid solution phase means the gamma nickel phase shows a greater sensitivity to the solute addition. There is no doubt, if we take a solid solution, if you keep on adding different alloying element, then the lattice parameter will change more. However, the misfit, the lattice misfit, it depends basically on two different parameters. Therefore, because if we add a ternary alloying element, then there will be a partitioning. So, it will prefer either to go to a gamma nickel phase or to gamma prime phase. So, the partitioning of the solute I between the gamma nickel and gamma prime phase. Now, influence of a particular solute on the lattice parameter, that is defined by the Vegard's law, that how much percentage of the solute or concentration of other alloying element to with the change of the lattice parameter, that basically explain the Vegard's law. So, now we can also look at the coarsening of the gamma prime phase that lose the coherency and increases the misfit. What I want to mean, that if you look at the microstructure, if you look at the morphology of this gamma prime phase, we can get a rough estimate whether the lattice misfit has increased or decreased. Means if we look at this 100 projection of a gamma prime phase in a gamma nickel matrix, this is a gamma prime phase in a gamma matrix, then if it is circular, then misfit strain or lattice misfit is less, but if lattice misfit increases, they will tend to make a cuboidal type of shape, and this is something very much interesting to notice. So, the degree of aging, if you increase actually, then the lattice misfit is also increases. This is just a one projection of the same particle from a different direction. So, if we increase the degree of aging in a nickel based superalloy, then lattice misfit will also increase. And we must think about why this lattice misfit is linked with the strength of a particle, because we all know the strengthening mechanism, right. And there are many different type of defect also available in this gamma prime phase. So, definitely point defect will arise and it depends on the temperature of the application. However, stacking fault is one of the very important major defect in gamma matrix also. So, in case of gamma matrix, we find that the for high temperature application, this stacking fault energy is one of the important consideration, because the screw portion of a perfect dislocation, they are dissociated into the Shockley partials and must constrict locally if they are to cause slip. And this is a very common mechanism which obstacle such a precipitate can be circumvented. It means that a widely spaced partial arising from a low value of gamma that basically stacking fault energy are advantageous for the high temperature application. What I want to mean, you know that if the stacking fault energy basically increases, then these are the two partial of a dislocation, the partial the distance between two partial will increase. Yes, this is a let us say low stacking fault energy example, and this is let us say high, because they have a higher line tension and so they can attract each other more. And here these are the two parameter, that is the stacking fault energy value and here is the creep strain rate. Okay. So, here these are the diffusivity and shear modulus Burgers vector with the temperature, and here we have the again the shear modulus and the Burgers vector. So, aluminum has a higher stacking fault energy, we all know about it, and you see that the creep strain rate is also higher. So, this is let us say in case of aluminum, and let us say this is in case of copper zinc, which has a very low stacking fault energy, something like 14 to 18 millijoule per meter square. So, pure nickel is lying here and we add chromium and all other alloying element, so that the stacking fault energy basically decreases as well as the creep strain rate decreases, and this is the purpose of the stacking fault energy in the matrix of the superalloys. Now, before going to this precipitation strengthening mechanism, we must try to recapitulate what is possible. So, you must have heard about that two different type of concept or particle nature that people consider, like a particle reinforcing in a matrix have two different feature, either it is deformable particle or it is a non-deformable particle. If it is a deformable particle, then the strengthening arises due to coherency or let us say misfit strain, and due to stacking fault energy, due to ordered structure, due to modulus effect, because dislocation if it has to pass through a lattice and let us say like a GP zone. Okay. So, there are coherent precipitate, it basically fluctuate the local strain field because of the modulus fluctuations. Okay. And interfacial energy and morphology, and also the lattice friction stresses. So, due to all these effect, basically a deforming particle strengthen an alloy. However, in case of oxide, nitride or other borides, if these are ceramic nature particle which are considered as a non-deforming particles, there we know about the OR1 mechanism by bypassing. Okay. And we have a very typical equation that says that the stress is linked with the spacing between the particle. Okay. So, if the spacing is higher, the increment of the stress will be less. However, if the spacing is very close, then we can increase the strength. So, here this is the Burgers vector and let us say G is the shear modulus. Now, in case of a deforming particle, the strengthening is linked with the antiphase boundary energy. Okay. Now, if we consider specifically for a ordered structure, how? Let us say this is a example of a ordered structure. We have A type of atom, B type of atom, A, B, and then you see that this is a boundary between a antiphase, means here I have another B and then I have A. Okay. So, this is a boundary between let us say a phase and a antiphase. So, this antiphase boundary energy is important, because if one dislocation passes through this phase, then we need another dislocation in order to make a antiphase into the phase. This is the phenomena of phase and antiphase in a ordered structure. So, in that case, when dislocation basically passes through a particle, then basically we need to consider this mechanism of strengthening. Whereas, in case of a non-deforming particle, this lambda or the spacing between these two is rather important. So, first what will happen? It will obstruct, dislocation will obstruct by the particles, and then let us say they will try, as the stress will increase, and they will leave a loop, and then they will bypass the particle. So, this is typical, let us say odd one mechanism of a widely separated obstacle. Now, very similar situation people have observed in case of a superalloy, when we consider a gamma prime phase nickel 3 aluminum strengthening. So, you can see that the dislocation they basically passes and cut through the particles. Okay. So, here these are the sheared particle of 140 nanometer in size, and they have a round, almost round like shape. So, you understand that the misfit strain is less, and now the ordered strengthening it basically appear when these dislocation travel into the matrix to form a antiphase boundary in the gamma prime phase. This antiphase boundary is removed by passing another dislocation, that I just said to a few minutes ago. Now, the antiphase energy represent a barrier which must be overcome by a if the particle cutting has to occur. Now, the antiphase boundary ordered strengthening can reach up to 400 megapascal, much higher than the strengthening by, let us say, modular stacking fault energy, interfacial energy, or let us say odd one mechanism. So, because of this ordered nature of the precipitate of this gamma prime phase, they provide the much higher strength level strengthening effect than any other kind of mechanism. However, if I consider a dislocation, the dislocation need basically two dislocation to make a antiphase into a phase, that I just explained a few minutes ago. Now, you consider these are the particles, and one dislocation passes, and then I have a antiphase. So, I need another dislocation to pass, and then only it become a phase, right. So, if this is a weakly coupled dislocation, then lambda will increase actually. So, the effective distance between two particles increase, so strengthening will be less, but in case of a strongly coupled dislocation, the strengthening effect is very high, because here lambda is smaller. So, you need to consider a effective coupling of the dislocation also. So, here these are just some of the micrograph that says that 8 nanometer size of pair that gives a effective strengthening actually. Now, very similar situation that I explained a few minutes ago, that we have a weakly coupled pair and we have a strongly coupled pair. Now, people have measured the increment of strength, and people observe that the mean particle radius is somewhat in the range of 15 to 20 nanometer, where we get a more effective strengthening, where there is a transition between these two different mechanisms. So, a higher level of ordered strengthening can be possible in this gamma prime phase strengthening. Now, if we consider that temperature dependent strengthening of gamma prime phase and role of gamma prime phase, we have to see this plot, and these are quite interesting plot. Usually, if we take any alloy and expose and at higher temperature and put some stress on it, then the strength of the alloy always decreases with temperature. That is already understood. In case of a gamma prime phase, you see that these are some single crystal superalloys tension tested around, let us say 001 direction, where the strength actually increases. let us say 800 degree centigrade. Please remember this temperature, and then it decreases. So, there are several examples like CMX series, this is a single crystal superalloy, and single crystal means it is basically a processing method. So, people try to understand why this strength increase is coming from, whether they are from the matrix or from the gamma prime phase. To look at, they have taken a single crystal mar alloy and single phase nickel 3 aluminum. You can see the increment of the strength is higher in case of single phase nickel 3 aluminum gamma prime phase. So, gamma prime phase is responsible for such kind of strengthening at higher temperature level. Okay. So, this is explained with this Kerr-Wilsdorf lock, that the cross slip segment act as a microstructure lock, because just a minute ago I explained about antiphase boundary energy and so on. So, if we have a APB antiphase boundary, then a dislocation actually movement is restrict, means if cross slip has to occur, they always stick to this antiphase boundary which is behind them, and they become immobile, and therefore, we get a increase in the strength of the gamma prime phase. Now, there are two zones, one zone here there is a increase and then there is a decrease. Why such phenomena actually occur? Here I show you one of the schematic that up to 1000 K, or let us say something like around 800 degree centigrade, the dislocation in gamma prime phase become immobile, that I said to you, and because of this Kw configuration, Kerr-Wilsdorf configuration. So, here these are the dislocation and there is a cross slip, and I have a APB here, okay, antiphase boundary, and they become immobile because of this cross slip. So, these are the cuboidal plane, and dislocation is moving in the 1-1-1 plane actually. So, they actually act as a barrier, this Kerr-Wilsdorf configuration, and increases the flow stress. However, above 1000 K, then again you have seen that the stress decreases. So, this stress decrease is linked with that the slip in this cuboidal plane here, these are the cuboidal plane increases, means cube planes are activated at higher temperature, which are not the primary slip system in a FCC. We all know actually that 1-1-1 are the planes of the major slip system of the FCC at room temperature, but at higher temperature this cube plane actually activated, and therefore, the flow stress begin to decrease. Above this temperature, edge and screw dislocation on the cube plane move without any cross slip, and therefore, the effective strengthening from the APB decreases. So, these are all about the Kw configuration. Here also I show you one of the stacking fault actually, and these two stacking fault due to two different partial, they are lying on this plane of 1-1-1, and I have another configuration of this kind of Kw lock. Okay. So, this is a typical Kw lock on a cuboidal plane. So, we can see that there are many different reason and mechanism involved in the strengthening in detail. So, thank you very much. We will continue the discussion in the next class.